Welcome back, everyone. Today we'll talk about two approaches to unsupervised learning. First, we'll talk about clustering, and we'll specifically look at an algorithm called k-means clustering. Then we'll take a look at autoencoders and see how they can be used to detect features. So far, we have only been talking about supervised learning. Naive Bayes, the perceptron, and nearest neighbors all fall in this category. The main idea is that we see some evidence and we make a prediction based on what we learned from the labeled data. This works when we have access to labeled data. In a way, the classifier memorizes the labeled data but is able to generalize enough to handle new examples. This looks a lot like this. Here we have supervised students who go to class. The instructor shows them how to solve a few problems, and eventually, hopefully, they're able to generalize what they were taught and solve new problems. Clustering algorithms, on the other hand, fall under unsupervised learning. They take unlabeled data and they try to detect patterns in this data. They try to group examples together. For example, they try to separate emails or images or customers into different groups without really knowing what these groups should be. This is useful when we don't know what we're looking for. We just have data and we want to organize it, hoping to get some insight into it. So this requires data, but no labels. That's easier to find. The problem is that we sometimes don't get anything useful. Instead of ham and spam, we get emails classified as morning emails versus evening emails. This is not as helpful. So the main idea is that we just feed the data as is to the clustering algorithm and let it figure it out. It's more like this kind of learning. So the main idea is that we have some examples and we want to separate them in different bins, in different clusters, where each bin holds similar things. Let's say we can plot our examples as points in a two-dimensional space. If we were to separate these points into clusters, we can do this. We have 4 clusters here. This looks right to us intuitively, but it's not the only possible grouping. We can also do this. So there's really no clear right answer. And the other big question is, what does similar mean? One option is to do what we did with nearest neighbors and use the Euclidean distance between the examples in the feature space. Similar examples are examples that have a small Euclidean distance between them. We can also use some other similarity metrics if we have them. K-means is the clustering algorithm that we'll study today. It's based on the following idea. We have the data examples, represented here by the individual balls, and we also have means. And the means represent the clusters. The means here are these little robots. We call them the cluster centers. The examples are assigned a group based on the cluster center that is closest to them. But that cluster center gets to move and lose some of the examples assigned to it, and it may collect new examples on the way. So the purple dots here represent data examples, and the red dots represent the means, the cluster centers. Here's the algorithm. We start with k arbitrary cluster centers. Then we repeat the following 2 steps. Step 1, each of the cluster centers, the red dots here, claims the data examples that are closest to it. So now we have this. Step 2, we move each cluster center to the center of the points that are assigned to it. So we move our red dots to the center of the points that are assigned to them. And we keep doing this until there are no more changes. So each iteration includes two phases. Phase 1, we update the assignments. We take each point and assign it to the closest cluster center. So let's say we have these 6 data points and 3 cluster centers. The cluster centers are the colored squares here. The arrows indicate assignment from a point to a cluster center. Now we take each point and reassign it to the closest cluster center. We get this. Some of the points' assignments have changed, not all of them. In phase 2, we update the means. We move each cluster center to the average of its assigned points. So here each square moves to a position between the 2 points that are assigned to it. Let's take a look at an example. So here the gray squares represent our data points. The colored circles represent our cluster centers. Step 1, we assign. So each square is assigned the color of the closest circle. So we get this, right? Each square is assigned the color of its closest circle. Now each circle will be moved to the average of its assigned points. So that red circle here has only one point assigned to it. It's going to move this way. For the green circle, it's almost in the right position. It probably needs to move this way a little bit. And this blue circle maybe needs to move up a little bit. So what we get is this, right? So the circles, the cluster centers, move to the average of their means. And then we repeat that. Now we assign to the closest mean. Is this square going to keep its green assignment? No, it's not, because now it's closer to the red circle. So this one is going to be lost by green, and it's going to be claimed by red. And we get this now. And now the red has to move, because the red has to move to be between the 2 points that are assigned to it. So red will move down, green will move down as well, and so on. So we repeat that until there are no more changes. And here's another example. Here the colors of the dots represent the assignments. The larger circles are the cluster centers. You can ignore the squares. The lines represent the direction where each cluster center is going to move next. So you can see that blue is going to move to the right, green is going to move up, black and red are going to move to the left, and so on. So here we start with 5 arbitrary cluster centers. 3 of them are kind of crowded here. So we're starting with a pretty bad grouping. Let's run the algorithm and let's focus on the red cluster center. So red moves to the left first, then it comes down, then it doesn't know where to go, then it kind of comes back and finally claims its own cluster. We actually end up with a pretty good grouping here. We have 5 well-defined clusters, even though we started with a lousy grouping. So how do we initialize our cluster center? Does it matter where we start? So let's say we start here. We end up with these 3 well-balanced clusters. But what if we start here instead? We end up with these 3 clusters. And this is not exactly what we want. So initialization is important here. Where we start determines which clusters we end up with. We are performing a local search here, so we may get stuck on something that's not very useful. And there are various schemes to prevent this. Some of these schemes involved using initialization heuristics. Here's an example where our local search gets stuck. We have 3 clusters here, but they do not represent the clusters that are obvious to us visually. The green and purple cluster centers share what we can see as one clearly defined cluster. The blue cluster center is claiming 2 distinct clusters. So why doesn't this work out like the earlier example when we had 5 clusters? Why doesn't purple move to the right to claim one of the 2 clusters that blue has? The main difference here is that we don't have points in between to make it possible for purple to move to the right slowly. There's no immediate neighboring state to move to, so we are stuck in our local search. So here are some questions to ask about our k-means algorithm. Will it converge? It usually converges relatively quickly, but it does not always converge to what we have in mind. Will it always find the true patterns in the data? The answer is no. But what if the patterns are very, very clear? In this case, it's more likely to find them, but there's still no guarantee. Will it find something interesting? Maybe. Again, no guarantee. Do people ever use it? Yes, absolutely. We use it to explore the data when we're not sure what we're looking for. How many clusters do we pick? The answer here is that no one really knows. We try different things, and some work and some don't work, depending on the data. Let's work through one k-means example. Here we have unlabeled data shown in the two-dimensional feature space. So on the x-axis we have F1, on the y-axis we have F2. And our goal is to apply the k-means algorithm starting with 2 cluster centers. K equals 2 means we have 2 cluster centers. And we want to identify clusters in the data. So we are given the initial position of the cluster centers. We have a pink cluster center and a green cluster center. And we need to answer the question, which cluster center is initially assigned to example A? So we look for the cluster center that's closest to A, and in this case, it's clearly the pink cluster center. The next question is which cluster center is initially assigned to example B? So here again, the cluster center that's initially the closest to point B is the pink cluster center. How many examples are initially assigned to the pink cluster center? So we need to look at all the points that are closer to pink. So this point here is clearly closer to pink. This one, we've already identified them. This point is also closer to pink, and this point is closer to pink. Now here we start getting closer to green, right? This point is closer to green, this one is closer to green, this one is obviously closer to green, and this one is closer to green. So it looks like these 4 points, 1, 2, 3, and 4, are assigned initially to the pink cluster center. And these 4 points are initially assigned to the green cluster center. We then move the cluster centers to the mean of their assigned points. What are the new coordinates of the cluster centers? So we basically compute the means. So for the green cluster center, we compute the average of the coordinates of the points that are assigned to it. So here for the F1 coordinate, we have 1 plus 1 plus 2 plus 4. And we divide by 4. The new F1 coordinate of the mean is 2. And for the F2 coordinate, we do the same. We have 2 plus 3 plus 1 plus 2. And we divide by 4. For pink, we compute F1. So we have 1 plus 1 plus 2 plus 5. And for F2, we have, this is here, is a 4 plus 5 plus 4 plus 5. And we get the new coordinates of the means. Which cluster center will then be assigned to example A? So now we have to reassign. This is our second iteration. We reassign. Well, A is still closest to the pink cluster center. So here A will be assigned pink again. B is still closest to pink, and B will be assigned pink again. Now, the top 4 points are all closer to pink, so these are all going to be assigned pink. These points are going to be assigned green. Where do we move the new cluster centers? What are the new coordinates of the cluster centers? So what happened here is that none of the assignments has changed. The points kept their previous assignment. So now the cluster centers are actually at the means of the points that are assigned to them. So there's no movement here. Our algorithm has converged. This does not always happen in one step. So you have to be careful if you ask a question like this. If there's any change in assignments, then there will be a move, then the cluster centers will move. In this case, there was no change in the assignments the second time around. Here is a real-world example of clustering. This is from Google News. Individual stories on the same topic, but from different news sources, are presented together. These are stories that are similar, but we can't train a classifier to look for a specific story because we don't know what the news of the day is going to be. So this is unsupervised clustering. Now, each cluster also has a summary, so after finding the cluster, we still have to label it, we have to summarize it, and this is yet another problem. Now, we also have top-level categories in Google News. We have world, we have US, business, technology, and so on. And here we have supervised classification. We can train a classifier here because the categories are fixed.